Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Humanity stands at an energy crossroads. As our civilization grows and our technology advances, our appetite for power grows exponentially. Today, our entire planet consumes roughly 28 trillion watts of energy annually. That sounds enormous, but consider this. Our sun radiates 386 billion trillion watts every single second. The total energy Earth receives from the sun is just 1 part in 2 billion of the star's total output. The rest disappears into the cosmic void, untapped and unutilized. This vast disparity between what we need and what's available led physicist Freeman Dyson to propose one of the most audacious concepts in theoretical engineering, a structure capable of capturing the sun's entire energy output. In 1960, Dyson published his revolutionary paper, suggesting that advanced civilizations might construct massive arrays around their parent stars to harness stellar energy. This wasn't science fiction. It was serious scientific speculation about the ultimate expression of technological capability. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. A Dyson Sphere represents the theoretical pinnacle of energy engineering. Picture a structure surrounding our sun at approximately 150 million kilometers, Earth's orbital distance. At this scale, the inner surface area would be roughly 280 million times larger than Earth's surface. Such a megastructure could theoretically capture nearly 100% of the sun's energy output, providing enough power to support civilizations spanning multiple star systems. But what would such a construction actually look like? Dyson himself never envisioned a solid shell. The gravitational and structural challenges would be insurmountable. Instead, he proposed a swarm of orbiting collectors, millions or billions of individual satellites working in concert to form a loose sphere around the star. Each collector would be positioned to maximize energy capture while maintaining stable orbits through careful gravitational dynamics. The energy implications are staggering. If humanity could harness just 1% of the sun's output, we would have access to roughly 4 billion times our current global energy consumption. This would enable projects previously relegated to science fiction, interstellar travel, planetary terraforming, massive space habitats, and computational power beyond current imagination. We could power particle accelerators the size of planets, support populations in the trillions, and potentially achieve the energy densities necessary for faster-than-light communication research. The materials required present their own challenges. Current estimates suggest that dismantling Mercury, the smallest terrestrial planet, might provide sufficient raw materials for a partial Dyson sphere. Mercury contains approximately 330 billion tons of material, primarily iron, nickel, and silicates. This would need to be processed into ultra-thin collectors, each optimized for both energy capture and structural integrity in the harsh environment of interplanetary space. Space-based solar power already demonstrates the basic principles. The International Space Station's solar arrays generate approximately 120 kilowatts of power using crystalline silicon photovoltaic cells. Scaling this technology to Dyson sphere proportions would require revolutionary advances in manufacturing, materials science, and space-based construction techniques. The efficiency gains alone, operating in the vacuum of space without atmospheric interference, would dramatically improve energy collection compared to terrestrial solar installations. The construction timeline challenges human comprehension. Even with fully automated self-replicating machinery, estimates suggest construction periods measured in centuries or millennia. This assumes breakthrough technologies in robotics, artificial intelligence, and space-based manufacturing that don't currently exist. Yet the potential rewards justify such long-term thinking, representing humanity's transition from a planetary to a stellar civilization capable of projects spanning cosmic timescales. Constructing a Dyson sphere confronts engineers with challenges that dwarf any previous human undertaking. The fundamental physics alone present obstacles that would require revolutionary breakthroughs in multiple scientific disciplines. Understanding these challenges reveals why such a project represents the ultimate test of technological civilization. The orbital mechanics of a Dyson Sphere swarm demand extraordinary precision. Each collector must maintain a stable orbit while avoiding collisions with millions of neighboring structures. At Earth's orbital distance, objects travel at approximately 30,000 meters per second. Even minor perturbations could lead to catastrophic collisions, destroying months or years of construction work. The gravitational influence of planets, particularly Jupiter's massive 12-year orbital period, creates complex resonances that could destabilize entire sections of the swarm over time. Materials science presents equally formidable challenges. Traditional solar panels weigh approximately 20 kilograms per square meter, far too heavy for megastructure applications. A complete Dyson Sphere using conventional photovoltaic technology would require more mass than exists in the entire solar system. Revolutionary materials like graphene offer hope. Single-atom thick carbon sheets with extraordinary strength-to-weight ratios. Graphene's theoretical tensile strength of 130 billion pascals exceeds steel by 200 times, while weighing practically nothing. Advanced manufacturing techniques would need to operate in the vacuum of space. Self-replicating machinery, sometimes called von Neumann probes after mathematician John von Neumann, could potentially exponentially expand construction capabilities. These machines would mine asteroids, process raw materials, and construct additional copies of themselves. The exponential growth phase could theoretically complete a Dyson Sphere in under a century, assuming perfect efficiency and unlimited raw materials. Heat management becomes critical at megastructure scales. Solar collectors operating at Earth's orbital distance experience temperatures around 127 degrees Celsius on the sun-facing side. Efficient heat dissipation requires massive radiator arrays, potentially doubling the structure's mass. Thermal expansion and contraction cycles could stress joints and connections beyond their failure points. Advanced heat management might employ liquid metal cooling systems or exotic materials with negative thermal expansion coefficients. Power transmission across astronomical distances poses unique engineering challenges. Microwave power transmission, successfully demonstrated by Japan's space agency JAXA, could beam energy across millions of kilometers. However, atmospheric interference limits efficiency, and beam divergence reduces power density over vast distances. Superconducting cables operating in space's cryogenic environment might maintain near-zero electrical resistance, but would require unprecedented lengths and structural support systems. The gravitational stability of individual collectors demands careful consideration. Each structure must maintain position relative to the Sun, while resisting gravitational perturbations from planets and other collectors. Station-keeping thrusters would consume energy and require propellant, reducing overall efficiency. Electromagnetic positioning systems might offer propellant-free alternatives, using the Sun's magnetic field for guidance and control. Construction sequencing presents logistical nightmares. The project would likely begin with automated mining operations on Mercury, the closest planet to our energy source. Robotic foundries would process metallic ores into ultra-thin collector sheets using techniques like molecular beam epitaxy or advanced three-dimensional printing. Transport systems would need to move billions of tons of processed materials across millions of kilometers, requiring breakthrough propulsion technologies. Quality control at astronomical scales challenges conventional engineering practices. Traditional inspection and maintenance become impossible when structures span areas larger than Earth's surface. Artificial intelligence systems would need to monitor structural integrity, identify failures, and coordinate repairs autonomously. Redundancy becomes essential. Losing even 1% of collectors to failures or collisions would sacrifice energy equivalent to thousands of nuclear power plants. The electromagnetic environment near the Sun presents additional complications. Solar wind, charged particles streaming from the Sun at 400 to 800 kilometers per second, could gradually erode collector surfaces. Coronal mass ejections, massive solar eruptions containing billions of tons of plasma, could damage or destroy unprotected equipment. Radiation shielding adds mass and complexity while reducing energy collection efficiency, creating fundamental trade-offs in design optimization. Building a Dyson Sphere would fundamentally transform our solar system, requiring the harvesting of entire worlds to provide necessary construction materials. The scale of this undertaking would eclipse all previous human industrial activity, by factors that challenge comprehension, turning planets and asteroids into the raw ingredients for humanity's greatest engineering project. Mercury emerges as the primary target for large-scale mining operations. This innermost planet contains approximately 330 billion tons of material, dominated by iron and nickel, with significant quantities of sulfur, calcium, and trace elements. Mercury's proximity to the Sun minimizes transportation costs, while its lack of atmosphere simplifies mining operations. The planet's extreme temperature variations, from 427 degrees Celsius during the day to minus 173 degrees Celsius at night, would require specialized equipment capable of operating in these harsh conditions. Advanced mining techniques would strip away Mercury's surface layers using techniques far beyond current capabilities. Plasma torches operating at temperatures exceeding 10,000 degrees could vaporize rock and metal, while magnetic separation systems would sort materials by elemental composition. The planet's relatively low gravity, 38% of Earth's, would facilitate launching processed materials into space using electromagnetic railguns or mass drivers. These acceleration systems could propel payloads to escape velocity without requiring chemical propulsion. The asteroid belt offers additional resources distributed across billions of rocky and metallic objects. Near-Earth asteroids like 16 Psyche contain vast quantities of platinum group metals and rare earth elements essential for advanced electronics. Robotic mining fleets would systematically harvest these resources, using ion drives for efficient transportation between targets. The total mass of the asteroid belt, approximately 4% of the Moon's mass, could supplement planetary mining operations while preserving larger worlds for future use. Processing facilities would need to operate at unprecedented scales. Imagine refineries capable of processing millions of tons of raw ore daily, operating continuously for centuries. Solar-powered smelters would melt metallic ores at temperatures exceeding 1,500 degrees Celsius, while chemical separation plants would extract pure elements, using techniques like electrolysis and fractional distillation. The waste heat from these operations could power secondary processes, maximizing energy efficiency across the industrial complex. Transportation networks would span the solar system, moving processed materials from mining sites to construction zones. Cycler orbits, trajectories that regularly connect different planets, could provide energy-efficient cargo routes. These orbital highways would minimize fuel consumption while ensuring steady material flow to construction sites. Automated cargo. Vessels, possibly weighing millions of tons when fully loaded, would travel these routes continuously for decades. The environmental impact on the solar system would be profound and irreversible. Mercury's gradual disassembly would eliminate one of the classical planets, fundamentally altering orbital dynamics and gravitational relationships. The asteroid belt's depletion would remove billions of years of cosmic history preserved in these primitive objects. Future generations would inherit a solar system reshaped by engineering rather than natural processes, with artificial structures dominating space previously occupied by natural worlds. Storage and inventory management present, logistical challenges on cosmic scales, processed materials awaiting construction would require secure storage facilities, protected from solar radiation and micrometeorite impacts. Automated inventory systems would track billions of components across millions of kilometers, ensuring the right materials reach construction sites at precisely the right times. Quality control standards would need to maintain consistency across materials processed over decades or centuries. The timeline for resource extraction stretches across multiple human generations. Conservative estimates suggest that completely. Mining Mercury would require several centuries, even with fully automated systems operating at maximum efficiency. This assumes breakthrough technologies in robotics, materials processing, and space transportation that remain purely theoretical. The project would need to maintain technological and institutional continuity across timescales that exceed the lifespan of nations and civilizations. Labor requirements, even with full automation, would dwarf current space programs. Millions of robotic systems would need maintenance, repair, and eventual replacement. Human oversight, though minimal, would require permanent populations in space-based facilities scattered throughout the solar system. These communities would develop their own cultures, economies, and possibly political systems independent of Earth-based civilization, creating humanity's first truly interplanetary society. The physics governing Dyson Sphere operations push against fundamental limits imposed by thermodynamics, materials science, and the basic laws of nature. Understanding these constraints reveals why stellar engineering represents the ultimate challenge in applied physics, requiring technologies that operate at the very boundaries of what the universe permits. Energy collection efficiency becomes paramount when operating at stellar scales. Perfect blackbody absorbers operating at the sun's surface temperature would reach equilibrium at approximately 5,700 degrees Kelvin, far beyond the melting point of any known material. Practical collectors must operate at lower temperatures, reducing theoretical efficiency through thermodynamic limitations. The Carnot efficiency, the maximum theoretical efficiency for any heat engine, depends on temperature differences between hot and cold reservoirs. Operating collectors at 1,000 degrees Kelvin, with space-based radiators at 300 degrees, would yield maximum theoretical efficiencies around 70%. Photovoltaic conversion presents alternative approaches with different physical limitations. Silicon solar cells demonstrate maximum theoretical efficiencies around 29% due to quantum mechanical constraints in semiconductor physics. Multi-junction cells using gallium arsenide and indium gallium phosphide can exceed 40% efficiency by capturing different portions of the solar spectrum. However, these advanced materials require exotic elements and sophisticated manufacturing processes that would challenge large-scale production. Thermodynamics imposes absolute limits on energy conversion and waste heat management. The second law of thermodynamics requires that some energy must always be rejected as waste heat, preventing perfect efficiency even in theoretical systems. For a Dyson sphere operating at stellar energy scales, waste heat rejection becomes a major engineering challenge. Radiative cooling follows the Stefan-Boltzmann law, with radiated power proportional to temperature to the fourth power. Doubling operating temperature increases cooling capacity by a factor of 16, but also increases material stress and thermal expansion problems. Structural mechanics at astronomical scales confront the fundamental limits of material strength. No known material possesses sufficient tensile strength to support a rigid shell at Earth's orbital radius. The gravitational stress would exceed the ultimate tensile strength of even theoretical materials like carbon nanotubes or graphene. This physical impossibility forced Dyson's original concept toward distributed swarms rather than solid shells. But even individual collectors must withstand enormous forces. Orbital resonances create subtle but potentially catastrophic instabilities in large swarm configurations. Jupiter's gravitational influence, though weak at Earth's distance, accumulates over time to create significant perturbations. The Kozai mechanism, a gravitational effect discovered by Japanese astronomer Yoshihide Kozai, can gradually increase orbital eccentricities until collectors crash into the Sun or escape the solar system entirely. Preventing these instabilities requires active orbital maintenance using propulsion systems that consume energy and reduce overall efficiency. Electromagnetic effects become significant when dealing with conducting structures spanning millions of kilometers. The Sun's magnetic field, though weak at Earth's distance, interacts with conducting collectors to create induced currents and electromagnetic forces. Solar wind, a stream of charged particles, generates additional electromagnetic effects that could gradually alter orbital parameters. Large conducting structures moving through magnetic fields experience forces described by Faraday's law of electromagnetic induction, potentially requiring constant corrections to maintain stable orbits. Quantum mechanical effects impose fundamental limits on information processing and control systems. Managing billions of collectors requires computational capabilities that approach quantum mechanical limits on information processing. Landauer's principle establishes minimum energy requirements for irreversible computation, while quantum mechanics imposes fundamental limits on measurement precision through the Heisenberg uncertainty principle. These constraints become relevant when coordinating activities across structures spanning astronomical distances. Relativistic effects, though small, accumulate over cosmic timescales. Time dilation effects near the Sun's gravitational field create synchronization challenges for precision orbital coordination. Gravitational redshift affects electromagnetic communications between collectors at different orbital radii. While these effects measure only parts per million, they accumulate over years and decades to create measurable discrepancies in timing and positioning. Material fatigue under cosmic radiation presents long-term operational challenges. High-energy cosmic rays and solar ultraviolet radiation gradually degrade material properties through atomic displacement and chemical bond breaking. Spacecraft materials typically degrade significantly after decades of space exposure. But Dyson Sphere components must operate reliably for centuries or millennia. This requires either periodic replacement, a massive undertaking at megastructure scales, or revolutionary materials with unprecedented radiation resistance. Thermal cycling stress affects all space-based structures, but becomes critical at Dyson Sphere scales. Components experience temperature swings of hundreds of degrees as they orbit between sunlight and shadow. Most materials expand and contract with temperature changes, creating stress concentrations at joints and connections. After millions of thermal cycles, fatigue failures become inevitable, unless designs incorporate sophisticated stress relief mechanisms or materials with unusual thermal properties. The fundamental physics of energy transport across vast distances creates additional constraints. Superconducting power transmission would require maintaining cryogenic temperatures across millions of kilometers, while microwave power beaming suffers from beam divergence and atmospheric absorption. Even fiber optic communications experience signal degradation over interplanetary distances, requiring sophisticated error correction and signal amplification. These physical limitations ultimately determine the practical size and configuration of any stellar engineering project. The completion of a Dyson Sphere would mark humanity's transformation from a planetary to a stellar civilization, fundamentally altering our relationship with energy, space, and our cosmic environment. The consequences would ripple through every aspect of human society, creating opportunities and challenges that reshape the very nature of civilization itself. Earth's climate would undergo dramatic changes as the Dyson Sphere gradually blocked increasing amounts of solar radiation. Even a partial sphere covering 10% of the Sun's output would reduce Earth's energy input by that same proportion, potentially triggering an ice age within decades. Atmospheric circulation patterns would shift as temperature gradients change, affecting weather systems that have remained stable for millions of years. Ocean currents driven by temperature differences might weaken or reverse direction, disrupting marine ecosystems that form the foundation of global food chains. The economic implications would dwarf any previous technological revolution. Energy costs, currently representing significant portions of global economic activity, would approach zero for space-based industries. Manufacturing could operate continuously, using essentially unlimited power, while transportation costs within the solar system would plummet as energy-intensive propulsion becomes economically viable. Traditional economic models based on resource scarcity would require fundamental revision when energy abundance eliminates most production constraints. Human population dynamics would shift dramatically as space-based habitats become energy-rich, environments capable of supporting millions or billions of residents. Zero-gravity manufacturing would enable construction techniques impossible on planetary surfaces, while unlimited energy would power closed-loop life support systems capable of sustaining large populations indefinitely. The concept of carrying capacity, the maximum population sustainable within given resources, would expand exponentially as energy abundance enables efficient recycling and artificial ecosystem creation. Interplanetary civilization would emerge as construction crews and support populations establish permanent communities throughout the solar system. These settlements would develop distinct cultures, social structures, and possibly political systems adapted to space-based living. Communication delays measured in minutes or hours between planets would foster local autonomy, while challenging traditional models of centralized governance. Economic specialization between worlds would create the first truly interplanetary economy, with each planet or region developing comparative advantages in specific industries or resources. The detection signatures of Dyson Sphere construction would be visible to alien civilizations across interstellar distances. Astronomical observations would reveal unusual infrared emissions as the structure converts stellar energy to waste heat. The gradual dimming of our sun, as seen from external vantage points, would create distinctive light curves, unlike any natural phenomenon. Radio emissions from construction activities and power transmission systems would generate artificial signals, detectable by sufficiently advanced alien technology. Humanity would essentially announce its presence to the galaxy as a technological civilization capable of stellar engineering. Scientific research would benefit enormously from unlimited energy resources. Particle accelerators could operate at energies impossible with planetary power sources, potentially unlocking new physics and enabling technologies like controlled fusion or exotic matter creation. Radio telescopes powered by stellar energy could conduct observations with unprecedented sensitivity and duration, potentially detecting signs of life or intelligence throughout the galaxy. Computational research would transcend current limitations, enabling complex simulations of cosmic phenomena that require enormous processing power. Space exploration would accelerate dramatically as energy constraints disappear. Interstellar. Probe missions become feasible when powered by substantial fractions of stellar output, potentially achieving significant percentages of light speed through advanced propulsion systems. The Breakthrough Starshot initiative currently plans to accelerate tiny probes to 20% of light speed, using powerful laser arrays, but Dyson Sphere energy levels could enable much larger and more sophisticated spacecraft for interstellar exploration. Social and philosophical impacts would challenge fundamental assumptions about humanity's place in the universe. The transition from energy scarcity to abundance would eliminate many sources of international conflict, while potentially creating new forms of social stratification based on access to space-based resources. Traditional environmental concerns would expand from planetary to stellar scales, as decisions about megastructure construction affect entire solar systems for geological timescales. Cultural evolution would accelerate as space-based populations develop new traditions, art forms and social institutions adapted to life in artificial environments. Literature, music, and visual arts would explore themes of cosmic engineering and humanity's relationship with stellar-scale technology. Educational systems would need to prepare citizens for a civilization where individual actions could affect entire planets and where technological decisions have consequences measured in millennia. The long-term trajectory toward even more ambitious projects becomes conceivable with Dyson Sphere energy resources. Stellar engineering could extend to neighboring star systems through interstellar expansion, while theoretical mega-projects like galactic-scale engineering become potential rather than purely speculative endeavors. Humanity would join the ranks of hypothetical Kardashev-type Type 2 civilizations capable of harnessing the total energy output of their parent star and potentially influencing the evolution of entire star systems across cosmic time.